After using the single-shot response for ISI analysis in your design phase, what's the next step? Right, eye diagram. But why is the eye diagram so important? We like to focus on why the eye diagram is a critical time domain tool in high-speed computation systems, from the initial circuit design to tape-out sign-off, then second validation and mass production QA process. As usual, in any circuit design, we must look at the time domain waveform and see if the signal is expected as the design target. But in a communication system, looking at the waveform at the TX SOC A and the RX SOC B isn't sufficient to evaluate if the error-free over target bit error rate, for example, YE minus 12, is doable. If we look at the waveform over time, you may see the amplitude level is different over different data samples in green, and there's no way for you to look at the 1 million bits and figure out the worst case over the minimum amplitude of the signal waveform. Similarly, you cannot capture the timing through different edge samples in red and figure out the worst case over the maximum peak-to-peak jitter from so many signal transitions. To further capture the transition time in the right fold time over the peaking ring behaviors in the wrong waveform visually, it's impossible. So, what can we do? Correct. Eye diagram. Chop the waveform in each bit time over 1 UI interval and overlay them, showing in 1 UI over 2 UI. As you can see, the eye diagram becomes a very useful tool for evaluating the timing or signaling for performance margin. For example, you can identify whether the CK data sample 1 over the CK data sample 2 is better to get the right decision or L-fit. Also, you can identify either the sample voltage 1 VS1 or the sample voltage 2 VS2 has a better voltage margin for the low bit error rate target. Combining both timing and signaling evaluation, the performance metric can be summarized by the eye width and the eye height easily. After understanding how to generate the eye diagram, then let's go through a few advantages of its usages. Think about the eye side images for 5 seconds. Bingo! The eye diagram helps us understand how the equalization EQ performance is. Last time, we talked about the single shot that helped us understand how the channel loss was. Then, we may know how to design or apply the equalization to remove or reduce the eye size as much as we can. At the end of the day, we must open the eye diagram to an open eye. So, during the design iterations, you can optimize your EQ design by looking at different eye performance in eye width and eye height margin. Since there is no perfect EQ to recover the exact eye opening before the channel, the designer should check different eyes and decide which version would be the final satisfied EQ design as the final tape-out sign-off. Besides the eye size, we need to have a complete signal-to-noise SNR link budget in a SerDes system, including other unwanted signals added into the noise category. Here is a case study of the eye-high margin evaluation from the handful eye diagram. For example, for most, the TX output swing 800 mV peak-to-peak differential and 22 dB loss are the nice rate in the PCIe Gen 3 specification, and we must apply the CTOE and DFE to equalize the ISI over PVT. Then, a worst case residual ISI shows 190 mV peak-to-peak differential in an eye high as a starting point. Second, the random noise from the circuit would be 5 mV RMS. Under bit error equals 1e-12 of the PCIe 3 specification, the peak-to-peak noise would be 70 mV from 14 times 5 mV. Third, the residual offset after the DC offset cancellation could be 10 mV peak-to-peak differential. Fourth, the SI and PI from the reflection, crosstalk, or supply noise would be another 10 mV peak-to-peak differential. Lastly, the sampler sensitivity could be 40 mV according to the required timing and the clock to Q delay at the target data rate 8 gigabit per second of the design. Therefore, the overall voltage margin of the eye high in the link budget would be 16 mV from the simple calculation. The useful eye diagram analysis in eye high for link budget will make you more confident that the whole link can meet the bit error 1e-12 for PCIe Gen 3 here. After getting the signaling link budget, we still need the timing link budget for the eye wave analysis of the eye diagram. Similar to the SNR concept in the eye high, we can get the eye wave by subtracting all the unwanted timing error and jitter. First and foremost, the TX total output high pass filter jitter RJ plus DJ from the jitter specification of most standards, the 30% UI is a must. Second, our EQ with CTOE and DFE ability shows the residual ISI related DJ is 12% UI. Third, the intrinsic RJ of the data path from the CTOE to the sampler after a high-pass filter at CDS bandwidth corner frequency shows 1% UI for PCIe Gen 3's bit error 1e-12. Fourth, are the DJs from the reflection, crosstalk, and supply noise shows only 3% UI owing to a good design exercise. Fifth, the sampler setup hold time may require 10% UI for the needed arrival time before, after the data transition. After figuring out the data path, sixth, we need to check other intrinsic RJ of the sampling clock from the CDR after a high-pass filter CDR's bandwidth corner frequencies, and that shows 3% UI for bit error 1e-12. Seventh, the intrinsic DJ of the sampling clock from the CDR's hunting jitter of the tracking behavior over supply noise introduced would be 12% UI in total. Lastly, most people apply multi-phase half-rate over one-quarter rate clocking, and the residual phase error could be 2% UI after the phase calibration to reduce the eye width further. Finally, the total eye closure in eye width is 73% UI, and the link budget of the eye width is 27% UI to make the link meet the error 1e-12 with a certain timing margin. Since the eye diagram is a two-dimension, we need a thorough two-dimensional link budget for high-speed studies. Interestingly, the high-speed eye is mostly diamond shape, which would correlate both eye width and eye height tightly due to the slow transition or small through rate. Therefore, we must move the eye of the residual eyesight only up and down by the thermal voltage outlier under the target bit array. Then move it left and right by the random jitter outlier as well. The interaction between the eye width and eye height shows the resulting 2D eye is precise enough compared to the bit array eye contour from the system simulation over secant validation. To make sure we could meet the target bit array, should we specify what the eye should be? Think about the eye mask image for 5 seconds. Bingo! Eye mask. Before looking at the eye mask, let's look at the eye diagram and transmitter of a study system. As you can see, the eye diagram can be measured through an oscilloscope directly at the TX output, which will show the signal integrity SI before the channel. Again, to meet the bit array and the target value, the most standard will define the eye mask to identify if the TX SI performance is acceptable for the link budget across any third-party service. 2 eye diagram images are shown here for your reference. The red one obviously shows the small opening and validates the standard eye mask. On the other hand, the green one obviously shows a wide and big eye opening and meets the standard eye mask with a certain margin. So, which one could meet the bit array easy? Right, green one. Again, when the chip came back after the verification engineer would apply the eye diagram on the secant and provide the data to the circuit designer for correlations. Of course, during the test validation, everything could be wrong, and the major eye diagram helps the debugging process either in the design or the testing programming settings. As long as the eye agrees between the simulation and measurement, the final TXI may be the final sign-off of the secant validation. In addition to the TXI mask, do we have the RX eye mask? Unfortunately, the specification did not specify the RX eye mask since the TX output eye mask and the channel loss profile in the spec should define the requirements of the RX input eye. Furthermore, the RX internal eye diagram after the CTOE or DFE would be handy, even though no specification defines it explicitly. The internal eye diagram and the RX is called eye monitor or eye scan, which is very handy for the design validation, so that the circuit designer can validate their designs and ensure that the system meets the required specifications for data transmission. According to the 2D bit array controls, the designers may have their own internal eye mask to meet link specification. In addition to the design phase, do you think the on-chip eye diagram is also handy in other usages? Correct. The on-chip eye diagram are useful during the testing or the bring-up phase in the chip validation. For example, the eye diagram can support secant correlation and binding. The eye diagram also can monitor on-chip variation to validate assumptions made from the simulation results in the design. According to our experience, the correlation between the measurement and simulation results is not aligned well because of the local OCD. If we can get the precise PVT information locally in the measurement, we can apply the same and precise PVT conditions into our simulation. Then, the strong correlation will not only help our design confidence, but also catch some discrepancies due to oversight bugs. Besides the validation from our design, what's the other benefit of the eye diagram in the test mode for ATE? Bingo! In the production task or ATE, if we could identify the bad parts and discard them, we can improve the overall yield by taking the eye diagram of the service during the production process. We may not boost the yield, but also reduce the screen cost. In addition to the circuit performance or plug defect, what's the other general concerns the eye diagram may mitigate? Think about the long-term link operation image for 5 seconds. Yes, reliability. The on-chip eye diagram improves the link reliability by continuously monitoring the PVT conditions. Any potential failures or degradation in the SI or EQ performance can be caught as early as possible, then allowing for the service to either stop the link and recalibrate the necessary blocks to prevent from the increased bit error or system damage. This proactive protection increases the overall link reliability without propagating the errors in the SoC system. Furthermore, the on-chip eye diagram provides accurate and reliable information about the service operation conditions to detect potential failures or performance degradation. Because of the system glitch, either in the circuit itself, or the environmental temperature or voltage variations that can result in thermal voltage stress and then chip damage. So, the on-chip eye diagram helps link management by providing accurate eye width and eye height readings across different lengths of the service link. Here are the summarized images showing you why you need an eye diagram for your design phase. Tape out sign off. Second, validation. Production or ATE test. And reliability enhancement. The eye can help you not only show the signal and timing, but also catch other unwanted qualities called noise. So you can evaluate the link budget well based on your recovery clocking and signaling in the eye diagram. To make sure the ecosystem works well, most specification also defines the TX output eye mask strictly. Besides the internal eye diagram, recent high-speed service as the internal eye scan or eye monitor after the CTOE or DFE for both design and second validations. In addition, the added internal eye monitor not only improves the yield during the production or ATE test, but also enhances the reliability in their lifetime. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.